Despite obviously being able to fly, we still don't quite understand exactly how butterflies fly. For example, when a butterfly flaps down then back up, isn't the amount of force produced throughout those two strokes the same but opposite? So the net force will be zero and hence no actual lift will be produced. Well, obviously not, because we know butterflies can fly. It's no secret. Or if it is a secret, then it's a terribly kept one. I mean, it's not like they're just reeling around on the ground. But what's more, even from what we can deduce and have tested, it is clear that butterfly wings are way bigger than they need to be in order to fly. What we do know is that butterflies flap their wings, and on the upstroke, the wings come together completely before being flung back down again. So while their flapping motion might seem quite similar to a regular bird's flapping motion, it isn't actually. For example, one major difference is that for the upstroke, birds are able to tilt each feather so that the air can go through the wing effectively, which reduces the resistance the entire wing has on the upstroke, and hence, throughout the entire flapping cycle, the wings produce a net positive lift. Butterflies, on the other hand, can't do that with their feathers, mainly because they don't have feathers. So in this podcast, we're going to cover in detail how butterflies fly. To do that, we're looking at this paper here called Butterflies Flying Using Efficient Propulsive Clap Mechanism Owing to Flexible Wings. It is open access, so you can find it in the link below. And this is something that this paper does, is it gives quantitative results about how much force the wings produce on the downstrokes and upstrokes and how the butterfly's unique wing construction affects those forces. So just first, quickly, let's cover some names for the different parts of the butterfly wings flapping motion because they will come in handy later on. So for the upstroke, this is called the clap or the clapping phase. And this is the general upstroke that has been described for about 50 years. Surprisingly though, in that time, we haven't really figured out what is going on here, but perhaps today we will. We'll just have to wait and see. Now, when the wings are at the top and of the upstroke and then they peel apart to then do the downstroke, this is called the flinging part. So this is the general motion of these wings. But in addition to that, is the flexibility of the wings important? And also, how flexible are these wings? So interestingly, at the top of the clap, when the wings are hit together, they are not just two flat plates hitting together, but instead the wings are actually flexing so that the edges of them hit before the central parts hit. This is definitely going to change how the air is expelled from the region in this cavity. So these researchers hypothesized that this will result in more force being produced, but we will have to wait until later in the results section to find out if this is actually true. So unless you're reading at home as well, the paper, then you can still skip ahead. But if not, then let's go through it here. So how did these researchers test these butterfly wings? So they actually tested real butterflies in a wind tunnel. They caught 6 butterflies of what they call the silver wash fritillari's family, which is pretty much a normal looking butterfly, but the wings are orange with black spots. So apparently then they weighed them on a scale, which I have no idea how you get a butterfly to stay still on a scale. Also, I wonder if you can actually get a fat butterfly. But anyway, and then between testing, they apparently these butterflies were kept in large enclosures, not the researchers, but the butterflies, with honey water to suck down, which honey water doesn't sound too bad either. So they tested these butterflies with 3D PIV in a wind tunnel. And it's incredible how you can always test animals in wind tunnels, how they come up with these mechanisms. So the way they did it here with these butterflies is that they had a small feeder in the wind tunnel, and this feeder was aligned so that it wouldn't really affect the flow, really reduce the amount of disturbance to the flow. There was a little bit of a disturbance, but they tried to reduce that. And then they had the wind going at 2 meters per second, which is actually quite slow for butterflies. Most butterflies can go up to about 6 meters per second or even higher, so they can actually fly pretty quickly. Then when the butterfly took off from the feeder, the PIV laser, which was located pretty far downstream of the insect, so that the insect wouldn't be harmed, would then capture the flow physics hitting it. So the PIV frequency here was 640 Hz, which is pretty good. And I must say that these researchers have done a really good job in explaining exactly what they did. So if you want to go into the finer details, then definitely read this paper. But even so, for example, they even noted the exact MATLAB function that they used to project the velocities and vorticity fields on certain planes. So they went into incredible detail into what they actually did. So to calculate the thrust and lift of the butterflies when they were flapping around, they integrated the wake to see how much the velocities effectively and the mass flow rates changed. And this is really cool because you rarely see such an approach to figuring out what the forces are of an object based on the wake. And obviously you can't attach a load cell to the butterflies, so integrating over the wake is also a very good way of going about finding these forces. Just one thing to keep in mind though is that because of viscosity, as you go downstream, the effects of the butterfly that it has on the air will drop as the additional momentum imparted onto the air will get converted into heat, and also vorticity will drop as well. So that is something that has to be kept in mind, because if you measure the wake 1 meter downstream, for example, then it is broken down a lot more than if it was just being produced, and hence the forces that you will calculate from, for example, these equations will be significantly different than if you had the wake plane higher, like further upstream or further downstream. So this is only one way that I know of that you can actually overcome this problem, and that is by calculating the velocity, potential, and stream functions of the flow. This is usually not possible for PIV because PIV samples only a small cross-section of the wake. And to actually calculate the velocity, potential, and streamline functions, you have to figure out what the flow is doing at the wheels as well, because those are the boundary conditions which you can then iterate through to figure out what's going on in the rest of the wake. So that method was actually pioneered by some researchers at Boeing in the late 80s and early 90s. And this was the method that I actually had to start using for my PhD to do effectively the same thing, but for airplane wings. And then later I used them for other projects as well, that kind of approach. From what I can tell here of their equations, they are not robust to the downstream length. So there will be some changing going on based on where they actually took this plane and how far up the butterfly was compared to the PIV plane. Now, I don't expect there to be too much of a change because butterflies are lifting off at the exact same distance from a PIV laser. But depending exactly which direction they travel on from there, it will change how long it takes for the wake to form, that's forming at the wings, to then hit the laser and hence change the calculated forces a little. Given the lengths we're talking about here, I would be surprised if the resulting errors would be more than about 5%. So let's just keep that in mind. Now, in addition to the actual butterflies, the researchers also made a mechanism called a clapper, mechanical clapper, to test if the wing flex affected the results, and if so, how. So they had rigid wings and flexible wings to clap through this mechanism, and we'll see later how this affected the results, to see if the actual flex of the wings changed the forces and the flow physics. So one thing that I'm not sure about in their experiments is that for the actual butterflies, the wind tunnel was run at 2 meters per second, and when it came to their clapper that they made, they ran the wind tunnel at only 0.2 meters per second. They say that they chose this velocity to keep the seated particles suspended in the air, so I'm not sure why they could run their wind tunnel much faster when it came to the actual butterflies without the seating particles dropping out of the air, but maybe it is to do with the different PIV setups. For those of you who don't know, the seating particles are the things that are in the air, which then reflect the light, the laser, and then you can then capture the images. If you don't have these seating particles, then you can't see anything. So anyway, let's move on to the results now. So in figure 1, we see some isosurfaces of the Q criterion, which essentially means that we are just seeing the vortices here. So this figure here. And they are colored in the vertical velocity, with the maximum vertical velocity seeing 1 meter per second and the minimum about -1. And this figure can be divided into two parts, the regions of blue and the regions of red. So the regions of blue are the wakes during the downstrokes, and the regions of red are for the upstrokes. And interestingly, despite the butterfly having 4 wings, because you have 2 wings on each side that are joined at like the abdomen area, so despite having 4 wings, there are only 2 loops, one from each side. So the 2 wings on one side act together in this case and create just one vortex loop. The downstroke wakes, so the blue regions here, that they occur during the downstroke, the flow is being pushed down because the velocity is downwards, and that isn't surprising. On the upstroke, the flow is being pushed up, and again, that isn't too surprising either. But what is surprising is that for the downstroke, this is apparently used predominantly for lift producing, and the upstroke is predominantly used for thrust producing. So that is quite amazing, because I don't know about you, but for me, I kind of think it is intuitive that the downstroke would be where everything is happening, both the lift and the thrust, and that the upstroke would just be wasted motion that wasn't necessary for the wings, but it just needed to go back into position. But evolution has made these wings so efficient that throughout their cycle, literally at every point, it's actually doing something important. So there is no wasted movement. And just quickly, I wanted to say that if you want to learn how to do OpenFOAM, which is a very powerful and free safety software, but hard to learn, check out our courses in the link below. We've had really good feedback on them, so we're quite certain you'll like them too and get a lot out of them. But anyway, let's move on with this podcast. So in figure 2, we see the quantifications of these thrust and lift productions. And I'm not quite sure what figure 2a is showing. So let me explain what I mean here. So on the x-axis here, we have the impulses in the different directions during the upstroke and the downstroke. IUST means the impulse during the upstroke in the thrust direction. IDST means the impulse during the downstroke in the thrust direction. And looking at these two values, okay, there is thrust being produced during the upstroke here, but the amount is much less than the negative thrust being produced in the downstroke phase. So from these values, it seems that throughout the entire cycle, the butterfly produced a net negative thrust, which means that it will be traveling backwards. I don't understand why we're seeing this. So from what I can tell, I think the errors of these measurements are too large, and what the values are showing here doesn't make much sense. So I mean, like, we know butterflies produce positive thrust throughout the flapping motion. So maybe something else is going on here, but I think it might be also just due to error. Anyway, the thrust production doesn't make much sense, but the lift production does. The IUSV value here means the impulse during the upstroke in the vertical direction, i.e. the lift, and the IDSV means the impulse during the downstroke in the vertical direction, so in effect the lift as well. And these values given here make much more sense than the thrust values, because during the downstroke it is much clearer that there is much more impulse being created in the lift direction and positive compared to the upstroke, where there is a little bit of negative impulse in the lift direction, so downforce. But during the upstroke, but like overall, this entire cycle, there is definitely a net positive lift, which makes complete sense because the butterflies can fly up, obviously. Now, there still might be significant errors in this lift production data, but at least the conclusions are logical here. Anyway, let's see, at least in figure 1, we can see here that the downstroke is more about producing lift and the upstroke is more about producing thrust. We can tell that from figure 1, that these two phases make the resulting vortex loops orient themselves differently in the flow. So during the downstroke, the vortex loops are oriented more horizontally, which makes sense when it comes to lift production. During the upstroke, the vortex loop is now oriented vertically, which also makes sense because it is more about thrust production. So at least that data really agrees with itself, and we can be fairly confident with what it is showing, and that the downstroke is more about lift production and the upstroke is more about thrust production. Also in figure 3, we see some information that supports these conclusions as well. So we see the vortex loops, but we also see the velocity in the free stream direction, which is colored in green. Notice that for the upright vortex loop, which corresponds to the upstroke, there is higher velocity fluid shooting through it and in the downstream and downstream as well. That means that the butterfly is throwing air backwards, and by simple Newton's third law, the butterfly must obviously be propelled forwards, so obviously thrust is being produced here. So that is the general aerodynamics of this butterfly and how the different phases of the flapping cycle produces different forces. What about the flexibility of the wings? Does that affect the aerodynamics and the forces generated, and by how much? So let's jump to that part now. In figure 4, so this figure here, there's a lot of information here, so let's go through bit by bit. So we see in figure 4 that the effects of the wings rigidity on the aerodynamic performance is not zero. There is actually an effect. So for the top figures, we see that for the flexible wings, so these two bottom ones compared to the two top ones, which are for the solid wings. So for the flexible wings, the impulse is much greater in amplitude, but only takes place for a fraction of the time that the solid wings impulse occurs for. So the solid wings seem to draw out this impulse, as opposed to the flexible wings really like boost this impulse and make it happen over a very short period of time. So overall, the flexible wing provides a much greater kick in the pants, while the solid wing produces a much more prolonged and smaller burn. In terms of the actual impulse, figure 4c shows that the flexible wings produce a much greater impulse too, so this right column here. However, the solid wings produce more energy per impulse, which I think is because it occurs over a longer period of time, I think. So the researchers found that this flexible wing had indeed a 22% increase in impulse, but surprisingly, the efficiency also jumped by 25%. That is really good. So these flexible wings are generally better overall. They also say that in terms of the actual aerodynamic flow physics, the rigid wings produced a double vortex loop structure, while in figure 3, we see a single loop vortex structure for the flexible wings. So there's only one loop here as opposed to a double loop. So while the wings that are flexible, the left two wings work together better, and the right two wings work together as well. Whereas for the rigid case, these four wings effectively act much more individually. So that also potentially is why we get a more efficiency for the flexible wings, because they work more synergistically. So that is a surprising finding, because there's also been some hypothesizing that a flexible wing allows the vortex loop to go into the cavity formed between the two wings when they start to peel apart when initiating the downstroke. So perhaps that is also true, but it is also true that the flexible nature of the wings allow them to work better together. And with that, we really end this podcast on a piece of wisdom from nature. So in order to work better together, you have to be flexible like shoelaces. If you're flexible like shoelaces, you can be tied together and make a larger shoelace that can then lace a bigger shoe. So if you want to learn how to do OpenFlow, which is a completely free and great safety software, check out our course in the link below. And we have one that goes from the complete beginner stage to doing your own DES simulations. We also have a course on advanced meshing, including sliding meshes, advanced dynamically morphing meshes, and overset meshes. And if you're doing aerodynamic experiments, did you know that there is a 2 to 4% error in your data and you didn't even know about it? In the Atmosphere Hawk link below, we go through the math as to why that occurs and what you can do about it to fix it. So that is in this podcast, and I'll see you next one. Peace, amigos.